I think because done very rush, so I think let's do it again. So we started on the tutorials on functional dependency last week. So that was, I remember this was the first question that we were doing. And I asked you all to try this. So let's go through this again. So the what we actually how to say, maybe just as a recap, for every database table, we have a list of so-called functional dependencies, and these allow you to define one entity to, in a way, imply the other. In terms of primary key, so let's say if it is a candidate key and my table is ABCD, my candidate keys immediately would imply all of A, B, C, D. So it would mean that for candidate keys, everything on my right-hand side is going to be every attribute on my table. So yeah, so something like that. So last week we started talking about functional dependencies, and then after that, we talked about in a particular table, right? There are in fact many functional dependencies that are possible. So I have A implies B. I have let's say in this AC implies D, whatever. So there are actually many of these functional dependencies that we can extract out from a certain table. So the next thing that we want to talk about is that what then is the minimal amount of functional dependencies that will help to define a certain relationship table. So that was where we stopped at last week. We went through the theory and some examples, and then we were stuck at question, not stuck, but we stopped at question 1. So right now, let's to do question 1, actually I ate into 5 minutes of the previous lecture. So let's redo that because I think it was done in a very rushed fashion. Okay, so these are the FDs that are given to us. This is the table, and the question is, what is the minimal cover? So the minimal cover, I think last week we had a few steps that we could do. The first step that we want to do is to decompose my right-hand side into single value attribute. Okay, so this is to ensure that my right-hand side is only has one single attribute. So A implies B, don't need to do anything. C implies B, don't need to do anything. AC implies D, don't need to do anything. What we need to do is actually all here, which is D imply A, D imply B, and D imply C. So these are the things that we need to decompose the right-hand side into single value attributes. Okay. The second step is the following. The second step, we want to check left-hand side for redundant attributes. So in this, right, this one, nothing to check because left-hand side only one attribute. Nothing to check, nothing to check, nothing to check, nothing to check. So the only thing we want to check is this. We want to check if AC implies D is both A and C essential or not. So in order to check for that, what we do is we will first assume that we don't have this rather we focus on this, and then we focus on finding the closure of A. Okay. The closure of A here is equals to A. Based on this is equals to B. And that's all. And closure of A does not imply C. Okay? So it means that I actually need AC. I cannot drop away C from this relationship. The next thing I do is I find the closure of C. Closure of C is equals to B and C. C and B. And I notice that the closure of C does not have A. So it means that in this relationship, I cannot drop off anything from my left hand side as well. So this is the, after step 2, I end up with this set of functional dependency. Okay. There is, after this, we have a step 3. Step 3 then deals with finding from these 6 functional dependency, is there any FD that is redundant or not? Okay, so let's do this one by one. So in order to do that, we need to analyze it one FD at a time. So let's do this. Okay. So I'm going to assume that A imply B is not there. And I will check to see if I'm able to find A imply B from the rest of my FDs or not. Okay, and we notice that A imply B cannot be obtained from the rest of my functional dependency. And so A is required. Next thing I find C imply B, this one. From my remaining, from this, I find that C imply B also cannot be determined from my functional, from my existing functional dependency. So C imply B will also be required. Okay. Okay. So maybe this one a little bit. Let's try to do one that we maybe it's not required. So let's look at D imply B. For D imply B, we will do the closure of B based on all the rest of the functional dependency. So we are going to check now if D imply B is required or not. So in D imply B, let's say I don't have this. I know that D imply A from here. I also know that D imply C from here. And D imply B also from here. And so because of this relationship, I know that this is not required. And so we donate this relationship. And so this will go on and if we go down this route, we will find that this is not required. D implies B is not required. Okay, so this is required, this is required. If I were to do AC, I would have A, C, B. I will not be able to find this relationship. So AC imply D is required. And if I were to check on this, D imply A, there's no way I can, I won't be able to infer this relationship. So D imply A is also required. And likewise, D implies C is also required. Okay. I remember last week, Ryan said that D imply A, B, C by itself is already a good enough cover already. So I actually actually did not verify that. I'm very sorry, but I did not verify that. Let's see if is this sufficient or not. Wait. I don't think so. Okay. Yeah, because I see it really like cannot like that lah. So anyway, yeah. So I don't think this one can. Okay. So yeah. So yeah, I don't think so also. Yeah, anyway, yeah. So we now have the minimal cover of this, and this. Okay, very good. But it's very good that you tried. So it's very I highly commend everybody for trying. Yeah. So it's very good. So this is the minimum cover for question 1, which I think we have it over here. Oh no, it's here. Oh, D imply, yeah. So only D is not required. Okay, so so this is for question 1. Okay, let's try question 2. So maybe you'll take how long you'll need? Maybe the next 4 minutes to do this question. Thank you. Actually, it's very strange because typically in class, right, I will be walking around the class to look at you all trying, but I cannot do it now. So I feel like I'm like very 做作. So, yeah, but typically I'll be walking around to kill. But now I also like cannot do anything. Yeah. There's step 1, step 2. Okay, the time is 8:45 and we'll start. So in the first step, we will decompose all the right-hand side into single attribute FDs. So I have A imply, D imply A, D imply C, and D imply E. So this is taken from here. Okay, so all these will follow. A imply B and AB imply C. So yeah, so this will be decomposed into single value FDs over here. Step 1. In step 2, I will check to see if any of these, I will look for the left hand side with more than one attribute. Only this one satisfied. So I will have to just check for A, B implies C to see if any one of this is redundant or not. Actually, this question is very clear. Because A implies B. So when A closure, right, I will immediately get A, B. So A immediately implies B. So I know that actually B is not required here. If I do the B closure, I'm going to get only B. And so B implies B, that's all. But from here, A implies B. And so in this, A, B implies C can be shortened to just A implies C. So let's do this. So now we end up with A implies B, A implies C, D implies A, D implies C, D implies E. And then the next thing we want to do is I want to find if any one of these is redundant or not. So I will assume that we do have this one first, and I'll find the A closure to see whether does it include B or not. So unfortunately, A closure is not unfortunately not. A closure is only A or C, so this is required. And now I'm going to look at this, and A closure is equals to A and B, and that's all. So this is also required. Now let's look at this tree. D implies A. So D implies A. I will assume that I don't have this. I will have D imply D closure. D will imply D, C, and E. That's all. I can't do anything else. So I think this is also required. Next one, D implies C. D implies C. I will again find D closure. D closure is equals to A, D, and E. But I know that I know that A implies B and C, which is A, B, C, D, and E. So D implies C is not required. So this is redundant. Okay. Last one, which is this one. This one actually is I think it should be quite clear that this is required. Let's do a check. So D closure equals to A and D and B and C. And so there's no E, so this is also required. So these three are, no, sorry, these four are the FDs that are required. Okay, so this is how we solve this question. Any question, any queries on this? Oh, I got a. Which slides are these? This is I haven't give you this one yet. Sorry, Jiawei, I haven't give you this one yet because this one got solution, so I never extract out the solution yet. But after today, I will put up the zip file today. Yeah, sorry about it. Yeah. Any other questions? So yeah, so this is not required. Okay. I think this is the last question. Then we move on to the lecture. So yeah. So what is the minimal cover? This one is a very long question. So maybe you all take it's actually a very long question. Maybe 7 minutes like that. It's quite tough, very tough. I tell you what, maybe you all do to step 2. Yeah, because I think you do to step 2 first, then we will break, and then I will then go to step 2, then we go together to step 3. Else like very long like that. Okay, let's do both step 1 and 2 together first. I have A, B implies C. I don't need to do anything here. Actually, this question is really quite long. And here is the first part already. D imply E, D imply F. So I'm done to here. I C imply A. Here. Okay, BE implies C. BC imply D. CF imply BD. A C oh sorry. CF imply B. And CF imply D. I also have A C D imply B. I have CE imply A, and I have CE imply F. So as you can see, right, actually it's going to be a very long question. Okay, now we have the first step done. The second step done is, so I wrote all these here because all these, right, I need to check if are there anything here that is redundant or not. Okay, let's go through this one by one. Let's try AB imply C. So over here is all the two value one. So actually two value one easier to check. Or rather, if we like check A plus, right, A closure, right, I don't need to look at all the two value one. I need to look at all this. So A closure is equals to A. B closure equals to B. So this is okay. So BE implies C. Okay, actually, you can notice that B and E, they don't appear on the left-hand side. So this is also okay. Let's just check off those that, okay, then these are the only two that don't belong anything on the left-hand side. Okay, let's look at this. B, C imply D. All can follow so far. B, C imply D. Okay, let's look at B closure is equals to B, nothing you can do. C closure equals to A and C. It does not imply B, and so BC imply D is also required. So now I have CF imply B, CF imply B, C imply A, and that's all. F is not present, so CF imply B is also required. In this scenario, CF imply D, C closure is also equals to AC. So AC imply D is, sorry, CF imply D is also required. Okay, let's look at these two before we look at this one, okay? So CE imply A, C closure equals to A of C. So A of C does not have E, so this is also required. Okay, notice that here we may be able to remove away this FD, but let's keep it here first because we're only in step 2. And let's look at the last one. CE imply F, and C closure equals to A of C, and so this is also required. Okay, so all these are required. Let's look at ACD imply B. A, C, D imply B. The easiest way to do it right now is to just consider them as individual items. So I have A closure, C closure, D closure. A closure is A, C closure is A, C, D closure is D, E, F. And so we find that C is able to imply A, which means that A is redundant here. And so we are able to reduce this to CD imply B. So we can remove away this A to make it CD imply B. So this is the end of step 2. Okay. Okay. So it's very messy. So that's why I have this set of slides that is a lot cleaner. So with this right, actually, then I can show slightly clearer lah, slightly clearer. So in step 3, we have to check to see if all of these are required or not. So in addition to this, I also have to check the single value, D imply E, D imply F, C imply A, and all of these other FDs. Okay? It's quite taxing, but that is how it is lah. Any questions so far? Okay, if there are none, we'll just look at I think we can actually go through it quite fast. Let's say AB implies C, right? AB implies C. The A and B does not appear on the left hand side of this tree, and it does not appear over here. So this is AB implies C is definitely required in step 3. Okay, so I'm using this to draw on step 3. Okay, because AB is not on the left hand side, so I can't fire off anything here. It's also not on my left hand side over here, so definitely it's required. Okay, let's look at the second one. BE implies C. BE is not on my left hand side of any one of these, also not on my left hand side of any one of these, so also is definitely required. Okay, so let's look at let's look at let's look at this one. D implies E. D implies E. So let's assume I don't have D implies E, and I find the D closure. D closure is equals to DF. And let's do is DF here. DF is also not here, and so that's all I can do. And D imply E is also required. D imply F. I find the D closure is equals to D of E. And is that all? It seems to be. DE is also not present in any one of these, so D imply F is also required. Let's look at C implies A. Let's assume I don't have this and find the C closure. There is nothing else here, so there's nothing else here, and so this is also required. Okay, let's go down this list again. BC imply D. BC imply D. Okay, so BC C is here. So if we look at BC closure is equals to BCA, and AB implies C. Okay, here. That's all. Okay, so it does not imply D anywhere, and so BC imply D is also required. Let me know if I screw up. Okay. Is everybody still following me so far? Okay. So for my cheat sheet, right? Actually, I don't want to go through all because quite repetitive. Right? For my cheat sheet, all will be required except for this one. So let's look at CE imply A. CE and look for the closure of CE. C closure equals to, from here, we already know that C implies A, so that's A over here already. Okay, and CE also implies F, so I also have a F over here. And of course, CF, which implies B and D, implies B and D over here. A, B, C, D, E, F. So actually, CE seems to be is able to imply everything. But in this situation, you notice that CE by itself implies A. So here we don't really need this because C implies A already. Okay? So we don't really need this to occur. It means that probably we only need, or rather we don't need this functional dependency at all. Okay, and actually from here we can also infer that a probable candidate key of this relationship is equals to C, because C implies A from here, and is that, let me see, did I screw up somewhere? No, I still C is actually a primary key. Yeah, so sorry. So no. But anyway, I don't need this relationship to occur because C already implies A already. So I don't need C E to imply A. So I don't need this as the functional dependency. CF, there's a question. CF imply B may not be needed. CF imply B. Let me see. CF imply B is not required. Let me check. Let me see. CF. Okay. So to see if CF is required or not, we find the CF closure. If we assume we don't have this and we find the CF closure, I'm not sure. So let's see. I know it's I know DF would be there, and D implies E and also F equals to C D E F. Question is CF imply B, is it? Okay, then CR, let's see. So CF implies C D E F. CD implies B. CD implies B. You are right. You are right. So because CD implies B over here, this is also not required. You're right. So this is also not required. Good. I think I didn't make any mistake. I think this is correct. Yes, very good. So CF imply B is also redundant. Okay. Any questions? All good. Okay, if all is good, I will share this set of slides in the Moodle after today. So I will, yeah. So I think that's about it. So what we will do is we will go on to the next lecture, but I think it's step 3. Oh, okay. Step 3 I still confused. Okay. Okay. I will go through. Okay. Wait. Let me see. Okay. Okay. Good that you ask. Okay. Let's let's go through what step 3 is. Maybe this example is too convoluted. So let's do a slightly less, yeah, this example is not so confusing now. So let's look at this. So step 1, step 2, right, breaks us down to A imply to a set of FDs that are minimal in terms of the attributes. So step one, it removes the attributes on my right hand side to be single value attributes. Step two, it cuts down my left hand side so that whatever attributes that are not required, it will be removed from it. In step three, I check to see if any of my FDs are redundant or not. Okay, so in step three, what we do is the following. Let's say if we want to check if this is redundant or not. So we don't know. So the thing we do is we would first assume that we don't have this FD, and then we take the left hand side and then we find the closure of the left hand side. And we find to see if from the other FDs that are remaining, if the closure of it contains my right hand side or not. Because if from my other FDs that are remaining, right, if the closure of my left hand side contains my attributes on my right hand side, that means that actually I don't need this functional dependency at all. So that is the thinking behind this. So let's look at this FD, right? I look at my left hand side and the closure. The closure of this is just equals to the value of A. And so I don't have my right hand side B. And so A imply B is required, is a required functional dependency. Okay. Okay, let's look at this one also. A, B implies C. A, B implies C. Okay, so because right now, right, we are testing A, B implies C. So we need to put back A, B implies C. We put back our earlier of A imply B here, and we are going to assume that we don't have this FD, and we find A, B closure, which is equals to A, B, and that's all. And we realize that A, B closure does not have C here. Oh, sorry, my second one is A implies C only. Sorry, yeah. Second one is A implies C only. So second one is A implies C. So I'm going to test if this FD is required or not. And I'm going to assume that I don't have this FD. And I find again my A closure. And in this scenario, my A closure is only A and B. So it does not have my right hand side here. And so I will need this FD in order to, yes, I need to calculate the closure all over again, yes. I will need this FD in order to recreate back my, or not, in order to get my functional dependency of A implies C. And so A implies C is also required here. Next one is this D implies A. Once again, I would remove away this. So you will notice I put back that one. So I will put the D closure, or rather I calculate D closure, which is D, C, and E. And notice that this does not have D implies A. And so D implies A is also required. So I will put back here Now I will remove this one, and I will have D closure, which is A, D, E, but I also know that A implies B and C, so this would be equals to A, B, C, D, E. And so in this case, D closure with all my 4 remaining FDs, I'm able to get back C even if I don't have this functional dependency. So it means that this functional dependency is not required. Because even without this functional dependency, I'm still able to get D implies C for my remaining 4 functional dependencies there. Okay, and so let's do the last one to be complete. The last one, I am going to see if D implies E is a required FD or not. I'm going to assume that D is not there, and I find the closure of D, and this will be D, sorry, D, and A, and A implies B, and A implies C. So notice that D implies D, D implies E is not in my closure, and so this is also required. And so D implies E is also required, and I have D implies E here. So I have, yeah, so that's how I get my 4 functional dependencies. Yeah, the algorithm not very efficient. So I don't know, is there a better way to do it or not? Yeah, so I also don't know. Yeah, so yeah. Anyway, this is how we do it. Okay, so right now the time is almost 9:20, it's 9:18. So let's do a quick 10 minutes break until 9:28. And I'll see you guys in a while's time. So before the last two lectures, right, we were talking about finding of primary keys, functional dependency, and actually all these, right, there's a key reason why we want to do all this. Recall in our first few lectures, right, we talked about wanting our tables to have no redundancy, to be to have like a single value attributes. So now, right, we are going to explain how do we achieve all these. And in fact, we achieve all these using functional dependencies. That is a topic which we are going to go through now, which is the schema decomposition, and the normalization of the schema. Okay, so hope I'm not too soft. So given the relation R and the functional dependencies F, there's a possibility of the relationship so-called having anomalies. So maybe redundancy. I think we went through this many times. And the ideal situation is to identify ways whereby we are able to split or decompose the relationship into several smaller relationships. And we split it more to have less redundancy or to apply to new relationships. So if you recall in the midterm, one of the questions we asked was that there was one table, or rather one database whereby actually it was designed in a way whereby we cannot join them together. So this is actually they call it a lossy decomposition, which means that my tables are decomposed, but there's no way that I can join back the original tables together. So that is a bad, of course, that is a bad design. Database design. Yeah. Today we are going to study the theory behind that and how we can identify such bad decompositions in a mathematical form. So I think we went through this many times already. So one of the ways that we want to split this up is that we can have position and salary as a separate table. So so we know that position implies salary. We also know that this implies this. So one way we can split this up is that I have just this table from here as one table, and then I have E number, position, and salary as my other table. Okay, so I think even in the first part of the course, we went through a little bit of this already, just that we did not go in depth into the theoretical part of what is determined to be a good split. Yeah, and we'll do it now. So let's look at this example. Assume that I have this relation with these attributes, and I'm going to abbreviate them as CJSJ, you know, like that. And let's assume that D implies this set of attributes. Oh, sorry, C implies this set of attributes. JP implies C, as D implies P. The idea is the following. If, let's say, I decompose my table into these two tables like this. Okay. So one thing is that this decomposition allows me to join back my entire table, entire original table. Okay, so this decomposition allows me to do that, but this decomposition loses a functional dependency. JP implies C. So J is over here, P is over here, C is over here. And in the way that this is decomposed, this functional dependency will be lost in this decomposition. Later on, we will go through an algorithm to automatically find out if are we losing any functional dependencies, or is our decomposition lossy or not. So later on, we'll go through an algorithm to do that. For now, it's just like a more of like a by eyeballing it. Okay. So let's do another motivating example. Okay. So for instance, I have this original table, flight number, departure time, arrival time, origin, destination. I will, let's see, I split this table up into these two forms, flight number, departure time, origin, and the other one is departure time, arrival time, and destination. So in this situation, the decomposition is actually lossy in the sense whereby I actually cannot join back these two tables. I mean, how am I supposed to join them? Yeah, there's no way for me to know how I join which row to which row. Yeah, so there's no way I know how to join back these two tables. So the decomposition is lossy. And then the functional dependency is also lost. So for example, flight number, it usually determines my, actually a lot of things. Flight number, it determines my departure time, arrival time, destination. I mean, departure time will still be fine because departure time is here. So, but the flight number to determine my arrival time and destination will be lost. Okay? So in this case, what is the attribute that is similar? Attribute that is similar is the departure time. Of course, it is not reasonable to assume that the departure time can be a good foreign key between these two tables. In fact, even here, I already have the same departure time already. So it's definitely not a good foreign key between these two tables. So this is a motivating example behind that. So the decomposition is not only lossy, but we also lose functional dependency. And let's understand what do this mean. Okay. Functional dependency means that lossy decomposition means that if we decompose the schema, original schema into S and T. So if I want to join back, or in this case, union back S union T, it does not give me back S, and S union T implies T. Both of these two are not in my functional dependency of my original table. Okay, so what this actually means is that I in I don't say in a very how to say straightforward way to understand is that you can just say that this doesn't give me back my original table. Actually, yeah, this is just a convoluted way of saying that this does not give me back my original table. So that's all. Okay, so lossy decomposition, you can think about it as this does not give me back my original table. Okay, so the other one is FD loss, meaning that if X imply Y, X and Y are no longer in the same relationship after decomposition. So this is the definition of a functional dependency loss. Okay. Okay. Let's go through some examples. Okay. I think with some examples, it will be a little bit clearer. Okay. This is going to be the algorithm. So let's assume that we have the following table: A, B, C, D, E. And then we are going to assume that these are the following FDs, and we split the table up into these two tables. Okay, so we will do a few steps. The first step we'll do is we'll draw a table that looks like this. Over here, we put in our table name R1, R2, and over on my x-axis, right, is all my attributes from my original table. We have this alpha over here. This alpha is there's a term to call this. This is called a distinguished variable. It's a very strange term. I also don't know why, but they call this a distinguished variable. I don't know why also lah. But yeah, it's just a very funny term. Yeah, but they call this a distinguished variable. So R1 has B, excuse me, B, C, and D, and so I put a distinguished variable on B, C, and D, and R2 has A, C, E, and so I put it at A, C, and E. Okay. So we put this at the distinguished variable, and okay, let's go to the next slide. So alpha is known as the distinguished variable. So the main objective, right, is that I want to be able to add distinguished variables through my functional functional dependencies until I have one whole row of distinguished variable. Once I have one whole row of distinguished variable, means that my decomposition is not lossy. It means that I'm able to recreate back my original table for my decomposed tables. Okay. Okay, I talked a little bit too much in this point. Is there anything that I can clarify? Okay. Basically, right, what we are doing now in lossless decomposition, right, is really just to find out whether are we able to get back our original table from our decomposed table. That's all. And this is the algorithm to do it. So step one, we draw this table. On my y-axis is my table name, decomposed table name. On my x is my attributes. Number two, I add distinguished variables of my attributes of my respective tables. Okay? And the next step is I try to add additional distinguished variables, but I have rules how I can add them. Okay, so these are the three rules that we need to have. Okay, this one looks very complicated, but actually when you do it in practice, it's very simple. Okay, so yeah, first rule, there are two or more rows of have distinguished variables belonging to a left-hand side of a functional dependency. It means that on my, let's look at this, two or more rows, left-hand side of functional dependency. For example, I have here, okay? And there's one or more rows have distinguished variables belonging to the right-hand side of functional dependency. So for example, I have a functional dependency like this. So on my left-hand side, I have two or more rows that have that belong to the left-hand side of a FD. So two or more rows that is of a left-hand side of FD attribute, left-hand side of FD. So this FD here. And on my right-hand side is one or more rows that is this has a distinguished variable with the right-hand side. So this is one or more row on my right-hand side, which is B. And my third condition is this. I want or more row from this with a non-distinguished variable belonging to the right-hand side of the FD. So there's one or more row, which is here, that has a non-distinguished variable belonging to one of the rows from here. So this means that I'm able to add a distinguished variable here. Okay, so this is what these three rules mean. It looks very complicated, but actually when you do it in practice, right, it's very logical. Means that I'm able to do a join based on my left-hand side of my functional dependency across these two tables. Yeah, so if you think about it in a very reasonable logical manner, right, it means that I have this C, this attribute that implies B, and this C attribute that implies B is crosses across two tables, table R1, table R2. And if I want to recreate back my B within my R table R2, I can do it by joining based on my attribute C. You understand? So let's say that if I have R1 is I know it's B, C, D, and R2 is A, C, E. And because I have C implies B, I am able to recreate this A, B, C, E. You see, it's like the closure, right? The closure of ACE, because B is also there. So you are able to get back A, B, C, E. But in this case, we call it like a distinguished variable because it's a lot easier to do it in this formula. And so I'm able to add a distinguished variable here. Okay. So is everybody clear how come I can add this variable here? I assume yes. Okay, let's say that I have another FD that looks like this. So if let's say I have FD1, FD2. Let's look at this again. So if I have this FD1, I now have two or more distinguished variable that belongs to my left-hand side of a functional dependency. This is my condition number one. If two or more rows that are distinguished variable belonging to the left-hand side FD, and I have one or more variable belonging to the that have distinguished variable belonging to the right-hand side of the FD. So this is the right-hand side. So it's one or more. And I have one or more rows from here with a non-distinguished variable on the attribute on the right-hand side of the functional dependency. And so this means that I can add a distinguished variable here. Okay. And let's say that I have another functional dependency here, which is let's say C also implies E. So on my right hand side, sorry, on my left hand side, I have two or more rows that have a distinguished variable belonging to the left hand side of a functional dependency. And I have one or more row with a distinguished variable belonging to the right hand side of a functional dependency. And I have a non-distinguished variable on one of the rows from the number one. And so I can add a distinguished variable here. So at this point of time, I have one row that has all distinguished variable, and this will mean that I'm able to recreate back my entire table from these two tables based on my functional dependencies. And so this is a lossless decomposition. Okay, Jia has a question. From condition 2, why does it say rows from 1 like condition 3? Or as one or more rows have distinguished variable, why don't it? Let me think. let me see. If let's say, I think do I need to have? I think I also need, Okay. It's a good question, Jia Wei. Let me see. Okay, I'm thinking if let's say I have this scenario. Let's say I have this scenario, right? I think I also need. I think I also need. Let's say I have this scenario whereby I have, let's say I have A, B, I have alpha, alpha, and I have alpha here. So I cannot add here. I cannot add here. Can I add here? I cannot add here. Hmm. Yes, I think I also need a form one here. Thank you, Jia Wei. Yeah, I also need a form one over here. So if let's say I have a situation that looks like this, I will not be able to add distinguish variable here. So yes, you are right. I need a form one here also. Thank you. Okay. But good means that you are also understanding. Any other questions? Yeah, maybe I edit now because yeah. Okay, let's look at the example. So in this example, I have A, B, C, D, E. I have these FDs. I split it into B, C, D, and A, C, E. Okay, let's look at the first. Okay, so in this, right, we can look at it FD by FD, no problem. Yeah, so in this scenario, we are looking at as as FD by FD. So let's look at the first FD. B AB implies C. AB. So the first thing we look at is the left hand side. Do we have two or more uh, rows with distinguished variables? So the answer is no, we don't have. So it failed. Okay. Let's look at the second one, which is C implies E. C implies E. We have two or more um, rows that have distinguished variables. So it passed the first condition. And let's look at my right hand side. Right hand side, I have one distinguished variable from my this one. It passes my second condition. And in the third condition, it passes also because there is no distinguished variable at least on one of my rows of my first condition. And so I'm able to add that alpha 1 here. Okay. Okay, very good. Let's look at C. We have done C implies E already. Let's look at B implies D. B implies D. Nothing we can do because there's B fails the first condition. So B implies D. Cannot do anything. Okay. So let's look at E implies A. E implies A. E passes the first condition. Because right now, I now have two distinguished variables on my left hand side of a functional dependency. So it passes the first condition. And then let's look at the second condition. On the right hand side, there's also at least one distinguished variable from the first condition. And on the third condition, there's also at least one non-distinguished variable on the row for my first condition, and which is this one. And so I'm able to add an alpha or distinguished variable here. So at this point of time, we see that R1 has entire row of distinguished variables. And so we can then conclude that this is a lossless decomposition. Okay. Does anybody need me to go through this? Sorry, let me just go through. Yeah, so this is all what I did already. Okay. The next example, maybe you take the next maybe 3 minutes to do this. Yeah, maybe you try to do this in the next 3 minutes. I do the first part already. Yeah, so just try the next part. Thank you. So I think you all don't need 3 minutes. I think 1 minute will be enough. Yeah, I'll start in about 1 minute's time. Okay, I will start. Okay, so this is the original table. There's one FD here, two FD here, three, rather first, second, three FDs here. So these are the two tables that are being generated. So firstly, for the y-axis, we put in the table names R1, R2. For the x-axis, we put in all the attributes from the original table. So C, S, J, D, P, Q, and V. For table 1, we have C, S, J, D, Q, and V. And so we put distinguished variables there. For table R2, we have S, D, and P. And so we put distinguished variables there. So now we actually, part of our work is already done already. So we just need to check for our three FDs whether are we able to add any other functional distinguished variables there or not. So in the first FD, we look at the left hand side. The left hand side does not have two or more rows that has the distinguished variable, so it failed. Okay, let's look at the second FD. In the second FD, it is J and P together. J and P together, it does not have two or more rows with both J and P together having the distinguished variable. And so together, this will also fail. Let's look at the third one, which is SD implies P. SP, which is SD, sorry, SD. So S and D. So S and D passes the first condition. It has two rows satisfying having the distinguished variables on the left hand side of FD. On the right hand side, it also has at least one distinguished variable from my first condition with a distinguished variable. It's only one. And it also passes the third condition where I have one row with a non-distinguished variable from my first condition. And so this will allow me to add a distinguished variable here and thereby creating a row full of distinguished variables, making this to be a lossless decomposition. Okay, so this is how we solve a problem like that. So yeah, the answer is given already. Okay, so maybe I should let's go through another example. Okay, so this is the original table. This is one single functional dependency. We are splitting it up into two tables, R1 and R2. In R1, we have F, D, O in my distinguished variables, R2, D, A, E in my distinguished variables. So I only have one functional dependency. How come no C here? No, this F. Right. Yeah. F. Yeah. So yeah. So F fails the. So this is not C. This is F. This is F. F implies DAOA. F on my left hand side fails the condition of distinguish two or more distinguished variables in my table, and so I cannot add anything, and so this is loss. It's a lossy decomposition. Okay, let's say we have alpha here. Let's say R2 F. Let's say R2 is instead of this, right? R2 is this. Okay, so maybe my question I want to pose to you all, right, is like that. Can I add the alphas here? What do you think? Can I add alpha here? Maybe I use it. Can I add alpha here? Can or not? The answer is yes, we can. because this is something like, my mouse is gone. This is something like Sorry, my mouse, my writing thing is gone. Yeah. Okay. Because this is something like F implies D, and F implies A, and F implies O, and F implies E. So this single FD actually is, if you look at this, right, this is actually F implies D, F implies A, F implies O, F implies E. So if you look at this from this kind of context, right, F implies A, and so this passes my two left, the two distinguished variables on the left side of FD, and this one distinguished variable on, and this one of my on the right side of FD, and one distinguished, and so I can add F. So although strictly speaking, the rule may not like apply here, but if you look at this as a FD, F actually implies D, F implies A, it implies this as a separately, and so I can still do the join on this based on individual attributes on my right hand side. And so if I were to have a table that is of this form, this decomposition, this will then be a lossless decomposition. Can I understand? Okay, let's I think we can do this one is a bit long. Yeah, I think today, I think that's okay for today. I think it's 10:07 and 10:08 already, and I think the next example I will eat up 10 more minutes of your time. So I think we will call it a day today. I will still be here to take any other further questions. Else, thank you again for your time this evening. So yeah, thank you so much for your time. I will speak to you all on Thursday. Thank you. I'm going to stop recording now.